the circuit. Here we will provide some voltage supply. Okay, let's suppose that this is some voltage plus and minus, and this is resistance. So the invisible energy which constitute the flow of electron in closed circuit is called the electric current. Okay, whereas this electrical potential is the work done divided by the charge. Okay, so here we can find out the electrical potential across these terminals. Across these 2 points we can find out the potential difference. Okay, so work done divided by the charge. And how you can represent this? Work done can be represented by W and charge can be represented by Q. So this potential is written as V is equal to W upon Q, and we can measure it in joules per coulomb. So now this is a simple representation of a wire, okay, and some current is flowing through that particular wire, a metallic wire, and some free electron will flow through across this particular wire. Okay, and we place this particular wire with some voltage supply. Let's suppose that this is the voltage V, and we are applying positive supply to this A side. Okay, this is the A terminal, and negative supply to this B terminal. So you can see the traditional flow of current, or you can say the flow of this conventional current is opposite to the flow of current. Okay, so electron will flow, okay, as you can see, oppositely to the conventional current, which is flowing from positive to the negative direction. Okay, a continuous flow of electron in an electrical circuit is called a electronic current. The current is the rate of flow of electron in a charge flowing per second. So how you can represent the current? I is equal to Q upon T. Energy supplied by the source. And what is source? Source is this battery. Okay, to each coulomb of charge is known as EMF. This potential difference is the amount of energy used by 1 coulomb of charge moving from one point to the another. So this particular energy, okay, this particular energy will move from A point to B point. Let's suppose that this is A point and this is B point, and this energy, 1 coulomb of charge, this particular charge is moving from one point to the another point. Okay, so this particular charge, or we can say coulomb of charge moving from one point to the another, is known as potential difference. So when you want to measure, okay, the potential difference, you have to consider the 2 points. This particular voltage source will generate the EMF. Let's suppose that this is a 12-volt supply right here, and from this we can generate the EMF. Okay, and we will find the potential difference across the 2 points. Let's suppose that we are considering A point and B point, and across this A point to B point, what is the potential difference? Clear, everyone? 1 ampere current is flowing through this, so B is equal to I into R. So this is 7 volt. Clear? Clear to all of you? Across this particular circuit. Okay, good. Is used right here to offer some opposition to the flow of electronic current, or we can say the current. Okay, it is the opposition for the current. And what is the Ohm's law? Ohm's law states that the current flowing through, or we can say between any 2 points of conduction is directly proportional to the potential difference across them. Okay, so how you can prove this Ohm's law? With the help of some resistance, you can prove this particular Ohm's law. So Ohm's law states that current flowing through or between any 2 points of a conduction is directly proportional to the potential difference across them. And we will provide some condition that temperature do not change for this particular Ohm's law. So we have seen this particular definition in the last lecture also. Is there any doubt related to this? So we can explain, otherwise we can move. Okay, so right here you can see the circuit. Right here you can see the circuit. This is the battery right here, and this is the resistance. Across this resistance, we will consider the 2 point A and B. Voltage is B. So mathematically, how you can prove this Ohm's law? Generally, Ohm's law represent B is equal to I into R. So how this B is equal to I into R will achieve? As you can see in the circuit, here we will provide some voltage. Okay, when you provide some voltage, current will flow through from positive to the negative direction. Okay, so according to Ohm's law, this current is directly proportional to the potential difference from point A to the B. Okay, from point A to B. So this current is directly proportional to the potential difference from point A to B. Clear? Okay, and temperature is, yes, temperature remain constant. This is the condition. This is the condition right here. Okay, I is equal to B upon R. So these two equations are going to be used so many times in your DC circuits. Clear, everyone? We have seen the limitation in the last lecture. We cannot apply this Ohm's law where transistor is used, electronic tubes are used. Okay, we cannot apply this Ohm's law to the nonlinear elements, okay, such as electronic arc or powdered carbon or silicon carbide. Okay, so we have seen these things also. Now come to the next point, which is resistance of a wire will depend upon. So first thing, let's suppose that this is your resistance. Okay, so first thing, this is the first thing. This resistance is directly proportional to the length. Okay, so let's suppose that its length is this. Okay, second point, resistance is inversely proportional to the area. Okay, so let's suppose that this is your resistance. Okay, this is the thickness of your particular resistance. So the area, okay, you can find out the area of this particular resistance. It is the inversely proportional. Okay, resistance is inversely proportional to the area. Okay, and nature, it will also depend upon the nature of the material. It will also depend upon the temperature of the wire. And when we will combine these two equations 1 and 2, so this resistor is directly proportional to the length of the wire and inversely proportional to the area. When we remove this proportionality constant, we can denote it by rho. Okay, so this rho is the resistivity of the wire, that is the proportionality constant. And how you can represent the expression of a resistance? R is equal to rho L by A, where L is the length, A is the area, rho is the resistivity of the wire. We have a length of let's suppose that 1 meter length of the wire is given. Okay, so specific length is given right here. Specific length is given. So this specific length of the wire will represent the specific resistance of the wire, provided the nature of the particular material and the temperature when it is in the use, it will depend upon these things. Okay. Yes, what do you mean by conductance? This is the statement right here. The loss of flow of current is called a conductance. Okay, it is the opposite for this particular resistance as conductance, and it is 1 upon R, and its unit is mho, MHO, mho. Okay, and symbol is opposite to the ohm. Okay, so when you represent OHM, its symbol is like this. So it is opposite. So you can represent MHO. So this letter will come first, then is second, then lastly O. Okay. So reverse is happening right here. This is the symbol for ohm and this is the symbol for mho. What is conductivity? It is the property of, okay, conductivity is a property. Generally, we consider this as a property, or we can say nature of the material, due to which it allows current to flow through it. Okay, and how you can represent this, as we know very well, this R resistance can be represented by rho L by A. So this resistivity, or we can represent this rho is equal to RA by L. Okay. Yes, same thing. Resistivity, conductivity, yes. It depends upon the nature of the material and the property of the material. If your material has a good quality of a particular material, then its conductivity is more. Okay, clear? Wire nature, yes. So this is the question you have to complete in this particular session. So here we have a wire of length 1 meter of resistance. Okay, specific length is given right here, 1 meter resistance. This is 2 ohm. Obtain the resistance. If specific resistance, we have to find out this specific resistance is double, diameter is double length. Okay, and 3 times the first time. Okay, so what we have right here, length is 1 meter. So this length L1 is represented as 1 meter. Resistance is 2 ohm. So this resistance is 2 ohm. Next is this P2, we can find out. Okay, so P2 is 2 times P1. Specific resistance is double. So we can represent this P2, that is twice of P1. Okay, specific resistance is double. So it's double to the first. Then diameter is also double. So this diameter is represented by D2. So this second D2 is double to this D1. Okay, so you can represent L2, length of the second wire, that is the specific length. It's a 3 times the first. This L2 is 3 times the first. So we have the formula R is equal to rho L by A. You can put this value. So you can find out this particular expression. And all of you, please give your response quickly. R2 is equal to 3 by 2 R1. 3 by 2 R1. Yes, Utkarsh, you are right. 3 by 2 R1. Okay. And you will put the value of R1 and find out the value of R2. Yes, it's 3 ohm. Yes, all of you. It's 3 ohm. Okay. And we will find dividing this R1 with R2. What we will get right here, 4 by 6. Okay, we will put all the values right here and we will get right here 4 by 6, or we can divide that 4 by 6 also. we will get 2 by 3. Okay, and we will arrange this equation. Either you will move R1 to the R2 side, or you can create 2 by 3 into R2, or you can also create this R2 is equal to 3 by 2 R1. Okay, and you can put these value of R1 and R2 right here. What we have in the previous slide, you can see the value of this R1 is 2 ohm right here, you can see. So you can put the value of R1 2 ohm. Okay, and you can divide this, and R2 will be 3 ohm. So this is the final answer.